Welcome to Chemical Reactions, Chapter 8, Section 3. This is the final presentation of Chapter 8. It is Part 5 simply because we have taken Section 1, broken that up into two different parts for the ease of just going into that information with balancing and with just general equations before that. Section 2 was its own thing. It was a very short presentation, and that was, I think, Part 3. Then Chapter 8, Section 3 has been broken up into two parts, Part 4 and 5. This is the last of it. And with predicting chemical reactions, when you know the reactant or reactants and then an arrow and then nothing after the arrow, how can you predict? It's a very valuable chemical skill, just as naming and formula writing is an incredibly valuable skill, and mole conversions, incredibly valuable chemical skills. So this is a really valuable skill. Your book starts to do some of this, but it is, I don't think it's as strong as it could be on how to predict. But yet, if you go into later chapters, all of a sudden they expect that you as a chemistry student all of a sudden have developed these predicting skills without really presenting it. I think that's one of the small weak points of your textbook. But because of single and double replacements as opposed to synthesis and decompositions are different, that I wanted to make sure it was in two separate parts. So this is the last of it, and this will cover both synthesis and decomposition reactions. And that's what this says, just another placard. Okay, the first thing we'll start off with is synthesis reactions. And synthesis reactions, and this also follows through for decomposition, by the way. But these are unlike the double and single replacements, where the double replacement only goes one way. Cations exchange, and then you just create the products. Single replacements, well, yeah, there's a no reaction part of it where sometimes the reaction doesn't occur. Otherwise, if the reaction occurs, there's only one way it goes. The metals replace the metals, the nonmetals replace the nonmetals. You predict, you write their formulas down, and balance, and that's it. However, with synthesis, that what we find is if you look at synthesis in a very basic way, that there are four different ways that synthesis reactions can proceed and form one single product. And you see those four on this particular slide. And by the way, in the handouts part of the Google Classroom, there is a handout that is a template. There are two of them actually. One of them is generic, where it's pretty much like this slide copied and the decomposition slide copied, and it's real basic. And then there's one where it has this information, but it also has examples worked out underneath each one of these types, so you can see what's going on there. And both are effective, and I would strongly encourage that you download them, and if you have the ability to print, great. Otherwise, that you have them ready to go when you predict, so you can predict confidently, and just basically use the template. It's all you have to do. So in this particular case with synthesis reactions, and granted that this is a very big simplification of the universe, does the universe only have four ways that synthesis reactions can go? Oh no, it is certainly much more complicated than that. But to keep things simple, but to yet give you the ability to predict, and that's an incredibly important skill set for chemistry, just like chemical naming and formula writing and mole conversions. All of these things are very important steps in becoming chemically and scientifically literate, that the ability to predict is certainly a commanding skill set. So it's a really good, powerful skill set. But we're going to keep it simple, and we're only going to talk about just four basic ways that synthesis seems to occur. All right, so I think my pen is activated. I got the color going. Okay, so let's check this out. Remember that all synthesis reactions result in one, well, actually, I'm going to need that space here, so let me get rid of that. Remember that they all resort in one product. That's the idea behind synthesis, one product. So how can you do that? Well, four ways. One, you can have two elements combining together, and they can make a binary compound. That's not too complicated to see. In the second example here, now it gets a little bit more to where we have some different combinations of things. We can have a metal oxide combining with water, and we can make what is called a base. Well, first let's backtrack and say, well, what is a metal oxide? Well, it's nothing more than exactly what it says. It's a metal combined with oxygen. Here are some examples. Let me give them to you, like sodium oxide, magnesium oxide, aluminum oxide. Those are all metal oxides, and it's literally that simple. Water, of course, no big deal there, and then they will form a base. Now, a base has an alternate name, which I use quite a bit, and it's actually a better name to use because it's called a metal hydroxide. And a metal hydroxide is just what it says. It is a metal like sodium combined with a hydroxide, or magnesium combined with a hydroxide, or aluminum combined with a hydroxide. And so that's what a metal hydroxide is, or sometimes it's called a base. Either way, it's a single product, and it's just the rearrangement of the metal and the oxygens and the hydrogens in water to form that metal hydroxide. The third way these reactions can go is you can have a nonmetal oxide combining with water. Well, let me erase this up here and talk to you about what a nonmetal oxide is, because it is, again, just what it says. So what is that? Well, a nonmetal oxide would be like dinitrogen trioxide, or dinitrogen pentoxide, or carbon dioxide, or diphosphorus pentoxide, those types of things. Those are all nonmetal oxides. Well, when they combine with water, they're going to make this really interesting compound called an oxyacid. We know what acids are. Acids are basically compounds that start with hydrogen. Well, an oxyacid is our ternary type 4 acids, our ternary compounds type 4 acids. And so that would be a hydrogen combined with a polyatomic ion. The polyatomic ion is a rearrangement of the nonmetal oxides. Think about those things can resemble polyatomic ions. So an example of an oxyacid would be like hydrogen phosphate, carbonic acid, nitrous acid. All of these are simply oxyacids, where the water has contributed an oxygen and the hydrogens, and the nonmetal oxide has contributed the materials for the polyatomic ion. And so all of that rearranges to give us oxyacids. So that's all they are oxyacids. And then lastly, down here for number 4, we have a metal oxide. We've already talked about that. A nonmetal oxide, we talked about that. And that makes an oxysalt. Well, what's an oxysalt? Well, certainly oxygen is going to be involved, but what is it? Well, really what it is, it's a metal that combines with a polyatomic ion that has oxygen in it. So examples would be sodium nitrate. That's an oxysalt. Barium, whoops, I was about ready to spell it there. Barium sulfate. Aluminum oxalate, 2043. So there's aluminum oxalate. All of these are oxysalts. It's a metal combined with a polyatomic ion. Where'd the polyatomic ion come from? From the nonmetal oxide. These nonmetal oxides rearrange to make polyatomic ions. And so that's where we can get our oxysalts from. So the star up here on number 3 and number 4 examples indicates that a polyatomic ion will form during the rearrangement of the nonmetal oxide. And that happens for oxyacids and oxysalts. Okay, so honestly though, metal oxides, metal hydroxides, oxyacids, oxysalts, how would I know all of this? Well, here's how you would know it. Here's how you can know it. This is a handout that you'll find probably in the Google Classroom into the handout section, and this will give you some chemical compound definitions that are much more specific than Stephen Zumdahl's type 1, 2, 3, 4, which is great for learning how to do naming and formula writing, but of course it's only unique to him and it's not used in chemistry at large. So what this particular handout shows you, it of course describes what a metal is, describes what a nonmetal is, reminds you of what a halogen is, and here is a metal oxide. What is a metal oxide? An ionic substance composed of a metal cation bonded to oxygen, and there are 4 examples of metal oxides. What is a nonmetal oxide? And 4 examples. What is a binary salt? With 4 examples. What is a binary halogen salt? With 4 examples. Here we go. An oxysalt. What is an oxysalt? And 4 examples. Oxyhalogen salt, which is kind of a take or a very specific type of oxysalt, which is again a metal combined with a polyatomic ion. That's just an oxysalt, and that's all it is. An oxyhalogen salt is a metal combined with a polyatomic ion, where that has a halogen in it. That's all. But because that halogen is really electronegative and it forms strong bonds, we have to look at it separately other than just lumping it into the oxysalts. After that, binary acid or a binary halogen acid, we kind of treat them the same. Here is the oxy acid we were talking about, where it's hydrogen combined with a polyatomic ion. Remember we were talking about bases? There's the base. It's a metal hydroxide. And so you see 4 examples there. And a reminder of the diatomic gases, all 7 of them. But really, I would want on that list phosphorus, arsenic, and sulfur, because they group together, they kind of clump together, 4 of these, 4 of those, or 8 of those, as they do. So they're not gases, but they are more than one atom at a time. So that's how you would know this, and that's a handout. So when you're looking down through these things and you want to say, okay, what's a metal oxide? You can actually look it up to remind yourself of what it actually is. Okay, so let's do some examples of how to predict with synthesis. So in our first example up here, I have 2 elements. That's all it is just 2 elements. So that's an element, and that's going to make a binary compound. That's just the template. That template is available as a handout. You can look it all up. And I label these things. Like I've done on this slide, I label them, and I go, okay, binary compound. That binary compound will be a sulfur phosphorus a strontium phosphorus combination. Strontium coming out of group 2 has a 2 positive charge. Phosphorus coming out of group 15 has a 3 negative charge. I would have to crisscross, so Sr3P2, and I would need a 2 out there to balance the phosphoruses, and I would need a 6 out here to balance the strontium. So 6, 1, and 2 are the coefficients, and that is now officially predicted as using the template. Okay, down here, what I see is potassium and oxygen. Potassium is a metal, and oxygen, of course, is oxygen. So that's a metal oxide, and this, of course, is water. A metal oxide and water make a metal hydroxide. So I'll just write that down. You can call it a base, but to me, metal hydroxide is probably a better term. And so what's a metal hydroxide? Well, that's going to be your potassium and your hydroxide. Potassium is a positive 1, hydroxide is a negative 1. They balance, so just KOH, that is it. To balance, I'd have to have a 2 out there. Okay, down here with phosphorus, diphosphorus pentoxide, and water, this now is a nonmetal oxide combining with water, and this will make an oxysalt. So, what do we do there? What do we do with this? Well, the excuse me, I said oxysalt, and I should say oxy acid, because water's there, so oxyacid. So what is an oxyacid? Remember, oxyacid is hydrogen combined with a polyatomic ion. That's all it is. So what about the polyatomic ion? Well, this polyatomic ion has to have phosphorus and oxygen in it. Does that suggest a polyatomic ion to you? Well, if you have it memorized, or if you're kind of familiar with them, you would say, wait a minute, there are only 2 that have phosphorus and oxygen, and that would be phosphite or phosphate. So it's kind of a 50-50 at the moment as far as which one would it form, because those are the only 2 options. Well, the one it actually forms, I happen to know, is phosphate every time. P2O5 will form the phosphate. So that would give me H3PO4. Positive 1, negative 3, crisscross, and it gives me phosphoric acid. Well, how did I know that? And moving forward on this other one, it's going to be the same situation. I got to figure out the polyatomic. How would I know that? Well, let's move the slide forward and see how I would know this. This is a partial list of polyatomic ions and where they come from. So where does a carbonate, figure out this first one here. So where does the carbonate polyatomic ion come from? And I'm going to have to change colors here if you want to actually see the... There we go. So maybe this color here, whatever color that is. So here is my carbonate. Where does carbonate come from? Carbonate comes from carbon dioxide that rearranges in a synthesis reaction to form carbonate. So carbonate can only ever form from carbon dioxide in a synthesis reaction. Sulfur dioxide will synthesize into sulfite. Sulfur trioxide synthesizes into sulfate, so sulfite and sulfate. And you may look at this again and say, well, whoa, wait a minute, isn't that sulfite? No, see, there's no charge. Okay, so there's no charge here. And so that is a type 3 compound. That's a nonmetal combination named with prefixes. And so that's sulfur trioxide, and it makes sulfates when it synthesizes. When the sulfate or the sulfur trioxide rearranges, it makes a sulfate every single time. As2O7, which is diarsenic heptoxide, will form an arsenate polyatomic ion. Chromium 6 oxide, if you look at that, chromium 6 oxide. Now I do know that chromium is a metal, but it functions here as creating a polyatomic ion, and so we're just going to name it that way at the moment. And it'll make a chromate. Let's see, manganese 7 oxide will make a permanganate. So this is how they synthesize. So you look at your nonmetal oxides here on this side, or anything on this side, and then you predict what polyatomic ion it'll form on this side. So notice the synthesis formation goes this way, and when we can use this chart, by the way, to go backwards and go decomp, but we're using synthesis. So how do I know that? Well, notice right down here at the very bottom, P2O5 synthesizes into a phosphate. So that's how I knew that. You wouldn't memorize this list at all. I've dealt with this list enough to where I've memorized some of it, which is nice and convenient, but it's not required to memorize. Notice in my next example, I'm going to need this one. So I have a dinitrogen pentoxide, and it's going to synthesize into a nitrate polyatomic ion. So here's that same slide again, but I advanced forward, so I lost all the writing from previously, but that's okay. I was at this one, we did predict this as H3PO4, and to balance, I would need to do this and do that, and I believe that now balances. Okay, P2O5 every time, phosphate. Now, aluminum oxide is a metal oxide. N2O5 is a non-metal oxide. This templates into what's called an oxysalt. And an oxysalt is a metal combined with a polyatomic ion, and the polyatomic ion comes from the non-metal oxide, just rearranges. Okay, well, I have this N2O5, so the polyatomic ion would have to have nitrogen and oxygen in it, and there are only two that I know of, and that is either nitrite or nitrate. So which one is it? Well, we already had looked at that, but right here, and I know it's hard to see on the white background there, but we have the nitrate. So I'm going to say that it's going to be an aluminum, and it's going to be a nitrate. And I'd have to crisscross, so AlNO3, 3. To balance, I would need to do a common multiple. Well, actually, 2 aluminums there, which then satisfies that, and then 3 times 2. So everything now balances, I'm pretty sure. Okay, so there you go. That's how you do synthesis reactions. I know that's not many examples, but it's 4. And there is a synthesis worksheet with an answer key provided with all of the predicting. And you can look down through those. And it does actually give you lines to where underneath the substances, like these up here, this would say, well, name this one. So you'd name that strontium. You'd name this phosphorus. And then you'd say, oh, this is an element and an element. And then over here, what's the name of the product? And this would be a binary compound. Here you would have said that's potassium oxide. And on the line below, you would say, oh, that's a metal oxide. And I think that last line is the really important one, because it helps you with the template. Then that tells you that this has to be a metal hydroxide. And, the naming is nice because that's practice naming is what that is. And that was the way it was built. But really, it's that second line down which allows you to figure out, oh, that's a metal oxide. This is water. It's got to be a metal hydroxide. This is a non-metal oxide. That's water. This has got to be an oxyacid. This is a metal oxide, non-metal oxide, and this has to be an oxysalt. So it's that last line on that worksheet that allows you to interact with that and label stuff and follow the templates more carefully. Okay, so there is synthesis. And then moving to decomp. Well, it turns out that decomposition is literally the exact opposite of synthesis. Synthesis is creating that one product, and decomposition describes how to take that product, make it a reactant, and break it back down again into smaller parts. So what you simply see here is literally the reverse of synthesis. And so number one, right down here, number one, take a binary compound and you break it up into two elements. That's literally the opposite. In number two, we take a metal hydroxide, excuse me, which is also called a base, and you break it back down into the metal oxide and water it came from. Number three, you start with an oxy acid and you break that down into the nonmetal oxide and water it came from. In number four, you have an oxy salt. Remember, a metal and a polyatomic ion, an oxy salt. Breaking that down into the metal oxide and the nonmetal oxide it came from. So those four are literally the exact opposites of the four synthesis reactions. If you can do the four synthesis going forward, you can literally reverse it and rewrite them in a backwards phase, and that's decomposition. Now, with decomposition, there is a fifth way that is unique to decomposition. You can't reverse this and make it synthesis. So what is that? Well, here is where we now have an oxyhalogen salt, which is a metal and a polyatomic ion, where the polyatomic ion has a halogen in it. So that would be like your perchlorate. Chlorine is a halogen. Perchlorate is a polyatomic ion with a halogen in it. Matter of fact, you only have three sets. You have the chlorine set, the iodine set, and the bromine set. So any one of those, that would qualify as an oxyhalogen salt. Okay, so when these break down, they do not break down like regular oxy salts. Why? Because the halogen has such a strong bond to the metal that it keeps the metal. It doesn't rearrange it all. It actually keeps the metal. And so what we end up forming is a binary halogen salt and oxygen. So one quick for instance, I know we'll have examples later, but let's go ahead and say we have sodium perchlorate. So sodium perchlorate, that is an oxyhalogen salt, metal, polyatomic ion, and a polyatomic ion has sodium in it, or chlorine in it. Well, when it breaks down, it's going to make a binary halogen salt. Well, a binary salt will be a metal and a halogen combination. Binary, two elements, halogen is there. There you go. So sodium chloride and oxygen, a very specific product here. Oxygen will form every time. And then balance. If we were doing this one to balance it, it would be just a 2 out there and it should self-balance. And now it balances. Now, that is different from an oxy salt. An oxy salt like sodium nitrate. When that breaks down, sodium nitrate is an oxy salt, no halogen. So therefore, the nitrogen does not have a strong bond to the sodium at all, and that's why the metal oxide, sodium oxide, can form, and then the other, then water can form, or whatever, or the nonmetal oxide can form. So it's a difference in that halogen. The halogen just creates a different set of strong bonding. And if you start with sodium chloride and you try and add oxygen to it, it won't react because the chlorine is so strongly bonded to the sodium that oxygen cannot incorporate itself into the compound to make that oxyhalogen salt we started with. So you can't reverse this. That's why it didn't appear in synthesis. How do we get then sodium perchlorate if you can't take these two and make them into sodium perchlorate? Well, you simply go through other processes to get sodium perchlorate. You just can't start with these reactants. That's all. Let's move on. Okay, just to remind you again of this handout where specifically here's your binary halogen salt, your oxy salts, your oxyhalogen salts, your oxy acids, your metal hydroxide bases. They're all up here as well as the metal oxides and the non-metal oxides. So this is how you can tell how those things are or what they are, and there's several examples there. So that's how you know, and that's a handout again available to you. Okay, examples. So I have to make some things up as we go here. So let's go ahead and make some examples up with decomposition. So a binary compound can be anything. Let's go ahead and do, say, MgBr2. Well, when I show that, Actually, let me do this. That's a good example, but I've got a better example because of the diatomics. So let's do AlBr3. Binary compound. It's going to break down into two elements, one of which would be aluminum and the other which is bromine. And bromine is now a free element and it's diatomic. That's, I think, the better example here. So bromine being diatomic, I've done what I need to do. I should balance. It's an odd even issue at this point. So 3 times 2, 2 times 3, and 2. So there you go. What about a base? Remember, a base is a metal hydroxide. So let's go ahead and do, how about calcium hydroxide? Calcium hydroxide is going to break down into a metal oxide, 2 positive, 2 negative, so just CaO, and water. So I don't have to do much there, but just say water, and then balance it. This one actually self-balances. An oxyacid. Well, an oxyacid could be H2SO4, sulfuric acid. Well, sulfuric acid is going to break down into a nonmetal oxide, and that would be a sulfur-oxygen combination, nonmetal oxide. But sulfate, what does sulfate break down into? That's where I need that list. So I'm going to go to my list. I have it inset up here. I need to change the color a little bit to highlight. And the sulfate line is right there. There's sulfate. And sulfate breaks down, so I got to read this chart in reverse, to a sulfur trioxide. So then this becomes sulfur trioxide. And again, water, you just write water down and balance. This one happens to self-balance. An oxysalt. An oxysalt could be, how about cesium phosphate, or phosphate. Let's do cesium phosphate. So here is cesium phosphate, and that will break down into a metal oxide, and so that's going to be a cesium oxygen combination, positive 1, negative 2, got a crisscross, so C2SO. And my nonmetal oxide has to be a phosphorus oxygen combination because it's the polyatomic ion that is breaking down and rearranging. So what is that one? Well, let's come up here. I still have it on my list. So over here on my list, here is the phosphite polyatomic ion, and it breaks down into a P2O3. So diphosphorus trioxide is my nonmetal oxide in that case. Balancing, oh, it looks like I need a common multiple here. So let's see, 3 times 2 is 6. 2 times 3 is 6 cesiums, 2 phosphoruses, and the oxygen's all balanced. So that one's good to go. Okay, with oxyhalogen salts. So let's do magnesium. Let's do bromates. So let's see, this is going to be MgBrO3. 2. I know this is an oxyhalogen salt because the bromine is a halogen and it's a metal polyatomic ion, which makes it that oxysalt anyway. When this breaks down, the binary halogen salt is the magnesium and bromine combination because that bond is so strong that it stays together. Magnesium is a 2 positive, bromine's a 1 negative, and so got a crisscross. And then oxygen, very specific, just like water when it forms, it's very specific. Then you would want to balance. 1 magnesium, 2 bromines, and the oxygens are not balanced, so 2 times 3 is 6, 3 times 2 is 6, and that balances. So here you go. There are several examples of decomposition reactions, and also showing the fifth way that these things go as well. This is just reiterating the fact that that polyatomic ion list, how you can read it going forwards and backwards. If you are in synthesis, you are going in that direction. If you're trying to decompose something, then you're going in this direction. Synthesis, you're starting with what I'm going to call a nonmetal oxide, even though I know that there are a few that are not exactly that. If you are decomposing, you're starting with a polyatomic ion, you're breaking it back down again. So this chart reads both ways, and this is how you know exactly without having to guess on anything. And there's a process by which, and do we always have to have this list? There's a 6-step process on how to know how to do this from scratch without a list at all. It's just beyond the scope of where we can go at this point in class together. So just follow the list, know how to use the list. Okay, here are some examples of decomposition. These are kind of mixed a little bit, so let's use kind of a template version of it. So magnesium perchlorate. magnesium perchlorate has a formula of Mg parentheses ClO4 2 positive, 1 negative. And I see that this is an oxyhalogen salt. Therefore, it's going to break down into a binary halogen salt and oxygen. So that's my template. Well, then let's make that. The binary halogen salt has to be the magnesium chlorine combination, 2 positive, 1 negative, crisscross, MgCl2, and then simply oxygen gas, and then you would balance this thing. I'm not going to balance, I'm going to move on because this is a very long presentation and we are so close to being done. So then you would want to balance. Okay, calcium hydroxide, the formula Ca parentheses OH2, calcium 2 positive, hydroxide 1 negative, you got to crisscross. Well, this is a metal hydroxide or a base, and that's going to break down into a metal oxide and water. And it doesn't matter if you put the water first and the metal hydroxide or metal oxide last. That part is irrelevant. It's just these are your two products. So the metal oxide is going to be a calcium oxygen combination. Calcium is a 2 positive, oxygen is a 2 negative, so they cancel, and CaO is the formula. And then just water. That one actually self-balances. Iron 2 nitrate. So iron 2 is Fe parentheses NO3 2, 2 positive, 1 negative, crisscross. Well, iron nitrate is a metal polyatomic ion combination, no halogen, and so this is an oxy salt. An oxy salt breaks down into a metal oxide and a non-metal oxide. Non-metal oxides, whenever they are involved, I have to invoke that polyatomic ion decomposition list thing. Okay, well, the metal oxide is pretty straightforward. It's going to be an iron-oxygen combination, and I don't have to guess the charge of the iron. Whatever charge it had as a product or as a reactant, it's going to have the same as a product. The single replacements didn't work out so well because the variable cation didn't have a charge at all as a reactant, and so that's why I had to guess that one. But these have charges, so there's no guessing. So that would be a 2 plus, 2 minus, and FeO is the formula there. The nonmetal oxide is going to be a nitrogen-oxygen combination, and this is a nitrate. So what does nitrate break down into? Well, I come up to my list up top, and here is my nitrate, and it breaks down into dinitrogen pentoxide. So N2O5 is how that would work. Balancing, well, actually I said I wasn't going to balance, but although that one actually looks like it balances. Okay, then lastly here, well, not lastly, next to last, manganese 6 fluoride, so MnF6. This is a binary compound. For all the big words that's the name, that's just a binary compound, and it's going to break down into 2 elements. So the first element is manganese, and I just write manganese. There's, it's not diatomic, so it's just Mn. No charges or anything because free elements never have charges. And then fluorine, but fluorine is diatomic, so I have to write F2 down. To balance, I would simply have to come up with the common multiple of, well, just 3 times 2 is 6. It's not a common multiple at this point. And that balances. Lastly, sulfurous acid, so H2SO3. Sulfurous comes from sulfite, SO3, and positive 1, negative 2, crisscross. This is an oxy acid. And oxy acids break down into nonmetal oxides and water. The nonmetal oxide must be a sulfur-oxygen combination, and sulfites, what do they break down into? Well, let's figure that out. Up here on the list, I actually have it, and sulfites are right there, and they break down into sulfur dioxides. So, sulfur dioxide is my, well, that's a huge 2 for a subscript, so that's a little bit better 2, and water. H2O, just got to write that down. This one self-balances, so hot diggity dog, there we go. Okay, so that's more examples of decomposition reactions, and again, on the synthesis worksheet, you will find that there are also decomposition reactions, and you have those lines again underneath where you can name it, and then you can write what it is, like a metal oxide or something like that, and that allows you to create the template. By the way, this template for decomposition is also available on the same handout that the synthesis template is, just reaction predicting template or something. So use it. Okay, so this is the end of the chapter. So end of chemical reactions. The test will be online or by packet. For juniors, let's see, for juniors, yeah, that's horrible. Let's try this one more time. For juniors, got to. Test is mandatory. For seniors, the test is optional, and it'll be posted in about a day or two. So that'll be available, and you'll be able to complete it by the deadline. Remember that we have graded work, and that's for anybody and everybody, but seniors, you may not have as much graded work as juniors. And non-graded work, that's optional. I'm not going to know if you did it or not, but the non-graded work would ordinarily be graded in class, and it is very important to developing that skill set. So you need do what you need to do, and that's all that last line says. I have one more slide, and if we have time, if I have a chance to post by the 18th for juniors only, we may, after Chapter 9, do just a brief intro to Chapter 9, and I don't know if we'll get to it or not. I'll know more in the next few days whether I'm able to get to this or not, but it would be intro. We would by no means be able to cover the entire chapter. It would be nice to introduce it to you. We'll see. That's it. That's Chapter 8 in a nutshell. Contact me certainly with any questions or comments. If you feel you need extra practice material for anything, by all means. Otherwise, keep up with the work and submit as necessary, and don't get behind on any of that. You want to be submitting in a timely fashion with all of that. So thank you, and we'll see you maybe in Chapter 9 juniors. Otherwise, hopefully I'll see any or all of you juniors in chemistry too. Looking forward to it. Really missed having you in class, and hopefully this has been at least an okay supplement. Okay, take care.